just introduce myself. And I'm going to talk about that, p-adic integration of the Hasse invariant. But before I get on to saying anything concrete, I maybe just want to begin by explaining maybe where we've got to in the seminar a little bit and where my talk kind of fits into what we're trying to do. So if you'll kind of allow me like 5 minutes of introductory waffle, and then we'll actually get on to some integration. So we've been studying these moduli spaces of Higgs bundles, and we've looked in particular at the SLN moduli spaces and the PGLN moduli spaces. And the upshot of this theorem that David wrote on the board at the end of his talk is more or less that these moduli spaces are SYZ mirror pairs. This isn't quite actually true. What's true is that this theorem implies that the corresponding Durand moduli spaces are SYZ mirror pairs via this procedure of hyperkähler rotation that we saw in Andre's talk. And so since these Durand moduli spaces, the SLN and the PGLN moduli spaces, these are going to be hyperkähler manifolds that are SYZ mirror pairs, and so by mirror symmetry, that I don't understand, this means that you should expect that appropriately defined Hodge numbers should coincide. And by appropriately defined, we mean stringy Hodge numbers that we saw in Wim's talk and that we saw in Bass's talk. And what Hasse showed in the same paper where they showed that these Durand moduli spaces were SYZ mirror pairs is they showed that in fact the Hodge numbers of the Durand moduli space coincide with the Hodge numbers of the Higgs moduli space. So in this case, the mirror symmetry conjecture tells us that these SLN and PGLN moduli spaces should have the same stringy Hodge numbers. And this is the conjecture that Gröcknig, Wiss, and Ziegler prove, and the proof of which is what we're trying to understand in this seminar. Now, if you cast your mind back to the very first day, in Johann's talk, he explained this proof by Batirev that birational Calabi-Yaus have the same Hodge numbers. And the sort of strategy of the proof was you first show that birational Calabi-Yaus have the same p-adic volume. You use this to deduce that they have the same point counts over finite fields, and then you use this to deduce that they have the same Hodge numbers by p-adic Hodge theory. And the kind of overarching strategy of the proof of this mirror symmetry conjecture is very, very similar. So somehow what they do is they prove that certain p-adic integrals on these moduli spaces coincide. They then deduce that the stringy point counts coincide, and therefore that the stringy Hodge numbers coincide. And so far, the kind of point we've got to is that in Bass's talk, we saw how to go from equality of stringy point counts to equality of stringy Hodge numbers. And essentially, the content of my talk is going to be how to go from equality of p-adic integrals to equality of stringy point counts. So that's the step that I'm going to fill in, and then hopefully in his talk, Dimitri is going to fill in the step of equality of p-adic integrals to complete the proof. So that's what I'm going to try and do. So, well, you've had quite a lot of intro already, but you're going to get a little bit more. So what's the basic setup we're going to look at? We're going to take S, which is the base from David's talk, to be the ring of integers in some finite extension of QP. Going to let K be the residue field. And we're going to assume P is coprime to everything. So there are going to be various integers appearing at various points of the talk, and whenever one of them pops up, you should assume it's coprime to P.
Unless it's P.
Pardon? Unless it's P. Or a power of P. Powers of P, I guess, might pop up at some point. Actually, no, Q is going to pop up, and Q is definitely not coprime to P. Because Q is going to be the size of the residue field. And we've got a smooth projective curve over F with connected fibers, geometrically connected fibers, and L on X, a line bundle of degree D. And what we saw in David's talk is on this SLN moduli space, we have this, I'm going to take an integer n, which is going to be co-prime to this degree D, and also co-prime to P, because everything is. And on this moduli space, we have this gerb, this mu-n gerb, and we have this gamma action, and this descends to, so let's call this, let's call the class of this alpha SLN, and this descends to a gerb alpha L on this PGLN moduli stack of degree D. And what we saw in Arne's talk was a formula for the number of points on a smooth variety. So, for example, this is going to be smooth over S. So we could write out, we have a formula for the number of points it has in terms of p-adic integration. It's q to the dimension times the integral over the OF points of some volume form. So this is the kind of volume form coming from the fact that, well, in this case, you can actually sort of write down a global volume form because these are going to be Calabi-Yaus, but in general, you don't even need a global one, as long as it's smooth. You can always glue them together locally. And kind of what we want to do today is, first of all, generalize this to stacky point counts. Sorry, stringy point counts. So, kind of what we want to write is stringy point count with respect to some gerb is going to be q to the dimension times the integral of some function f alpha depending on the gerb with respect to some measure. And I'm going to explain kind of where all these pieces come from. So this can be some orbifold measure that I'll define later. And then the second point, although really for the first point to be useful, we're going to need number 2 is describe this function explicitly. So that's the goal for today. And so now what we're going to get is going to be a formula for these stringy point counts. And I guess in one sense, even in the SLN case, we don't get anything new, right? Because it's smooth, and so the stringy point count is the same as the usual point counts. But nevertheless, the more complicated formula that we're going to write down is still going to be useful in the SLN case. Right. So let's get going properly now. I'm going to talk a little bit about a construction that appears in this paper called transgression, and then use it to kind of remind you of this of what the stringy point count actually is. Just because some of the constructions that we see along the way are going to be useful later on. So we're going to fix some quasi-projective scheme over S, and we're going to assume that it has an action of a finite abelian group, which is generically free. So the example to bear in mind is M is the SLN moduli space, and gamma is the n torsion in the Picard group. Or the other example that we're going to use is n is the SLN moduli space, and gamma is the trivial group. and we're going to let curly x be the static quotient, and then x be its coarse modulo space, which is the actual quotient. And we're going to take some germ living on the quotient stack, some mu n germ where n is the same integer as above. So this, this corresponds to some germ on x. Now we saw r and n appearing in David's talk. I'm actually going to fix some different r, which is the lowest common multiple of the order of gamma and n. And again, this is going to be co-prime to p. I'm going to fix some primitive r root of unity in field F. Since we're going to use point counts, we're going to see étale cohomology appearing, and so we're going to also need to fix an auxiliary prime L that's going to be provide a coefficient field for étale cohomology, and we're also going to fix an isomorphism between QL and C. So now our root of unity zeta induces a canonical character of mu r f, which is equal to mu r k, with values in either C or QL bar. So this character sends zeta to e to the 2 pi I over r. Right, so we've set up a lot of notation. And in order to be able to describe transgression, we need to know what an inertia stack is, which we saw in Vessel's talk, I think. But I'm just going to quickly give the definition again. So Ix is the inertia stack of x, which is given by pairs xf, where x is an object of x and f is an automorphism of x. So this is a little bit imprecise. You should read this as apply this to s points of the stack x for all s. A couple of examples of what this inertia stack actually looks like is if we take the classifying stack of gamma over this residue field. Right, well, what's an object of this stack? An object of this stack is a gamma torsor. What's an automorphism of a gamma torsor? Well, an automorphism of a gamma torsor is just multiplied by some element of gamma. So what you can see is the inertia stack, in this case, is actually a disjoint union over, I mean, it's really, what it really is gamma cross B gamma. This is the object, and this is the automorphism. Okay, so that's one example. A second example that's going to be important for us is if we take an abelian extension of f, and gamma is the Galois group of L over f. And we define a stack x L over f to be the quotient of the ring of integers in L by gamma. So if you look at this, its generic fiber is just spec O of f, but its special fiber has some stackiness that measures how much this extension is ramified. So what you can see is that the inertia stack of this, if I take its generic fiber, well, it's just going to be spec of f. The inertia stack of a scheme is just the scheme itself. And its special fiber of this inertia stack is going to be isomorphic to, the special fiber n is going to be isomorphic to the inertia stack of the classifying stack of the inertia group of this extension. So I'm going to write this slightly differently. I'm going to get a number of copies of the classifying stack of the inertia group of L over F indexed by elements of the inertia group. Okay. And now what happens is that this primitive root of unity essentially gives us a canonical k point of this right-hand side, right? Each of these factors, if you like, each of these factors has a canonical k point coming from the, map from spec k to the classifying stack, and this zeta picks out one of them by class field theory. So local class field theory gives us a surjection from mu r of f onto this inertia group, and so via this, what we get is a distinguished point let's call it y zeta in the inertia stack of this x L over f. So zeta is in here, it maps for an element of here, and an element of here gives us, tells us which factor to take. Okay.
Is R now multiple of the ramification?
Pardon?
Is R a multiple of the ramification?
R is the lowest common multiple of gamma and n.
Oh, sorry.
Yes. Okay, right, so this is a little bit on inertia stacks, and then what this construction of transgression gives is a way from going from mu n gerbs on x to mu n torsors on the inertia stack. So I'm just going to explain a little how this works. This is some kind of construction that takes in a mu n gerb on our stack x and spits out a mu n torsor on the inertia stack. So how does it work? Well, let's suppose we've got our mu n gerb. So this is our kind of gerb whose class in cohomology is alpha. Then if I take any y point, so I don't know, let's call this, I don't know what to call this map, let's call this map P. So if I take a y point, then what you can see is that because this is a mu n gerb, we have an extension of, well, we in fact have a central extension of groups where we can view automorphisms of y in y as an extension of automorphisms of the image of y in x by mu n. And essentially this is just what it means to be a mu n gerb, more or less. And so, kind of, if you like, we have mu n torsor over automorphism groups of p of y. And these automorphism groups are nothing but like the fibers of the inertia stack over schemes. So in other words, kind of from any so what happens is that all these mu n torsors are now going to glue together to give a mu n torsor on I of x. Okay, so these all glue together to give a mu n torsor. What am I going to call it? Let's call it T alpha. And let's call this map pi alpha. Over the inertia stack. Because somehow what happens is that right, there's a natural map here, and as soon as I pull back to a scheme, then the fibers is an automorphism group. And over that automorphism group, we've got our mu n torso. And then these all kind of glue together in a nice way.
Is this map at all injective or surjective? I mean, everything should be canon. Sorry, there's no reason you should know.
I have no idea.
Okay.
On a scheme, it's going to be the trivial map, I guess.
Right. I would imagine so. Yes.
So,
okay.
or if there's no extension between the odd and the mu, and it will also be an.
Yes.
Yeah, you take the fiber over F, right? You have a pair X, comma F as on the upper blackboard, and the inverse image of F is your torso. So if F is the identity,
then thank you. Okay, and now we can use this to kind of sort of remind ourselves of the definition of the stringy point counts, because what we do is we take the push forward along pi alpha of the constant sheaf. This is going to be some sheaf on the inertia stack. So it's also going to have an action of mu n, right? Because T alpha is a mu n torso. But we also have a canonical character. Yes, chi induces a character of mu n into QL bar, so we can take kind of the chi isotropic part of this. And this is going to be basically a rank 1 least sheaf on the inertia stack of X, and then the stringy point count is somehow a kind of suitably weighted point count twisted by this sheaf on the inertia stack. So if MS is over, I'm going to assume M is smooth over S, but I'm not sure how. I'm not qualified to explain how necessary this assumption is. Then the stringy point count of X is the thing we get by kind of adding up the traces of Frobenius over all the points of the inertia stack, suitably weighted. So we go over all k points of the inertia stack, we look at the trace of the Frobenius of y acting on the, I didn't give this a name, let's call it L alpha. We look at the trace of Frobenius acting on the stalk of L alpha at y, and then we weight in the appropriate way. So the correct way to weight it is by the fermionic shift and by the automorphisms of y. So this is fermionic shift that I think pops up in Basse's talk. It's closely related to the weight that we saw in Wim's talk, but it's not quite the same thing. It's very, very close though. And there's a simple formula relating them. Like one is like n minus the
Q
other.
is equal to x times y, right?
Pardon?
If Q is equal to x times y, you have the other one. Is there any other difference?
I guess not. Yeah, it's like the fermionic shift is like n minus the weight, I think. It's like dimension minus the weight.
Yeah, well, somehow I think you also have to be careful with, because it's all cohomology with compact support, sometimes there is a little shift.
Ah, yeah.
And there is a one,
Yeah,
but
yeah.
apart from that, it's really the same.
Okay, so
And if
I'm
it's
not
not the same, then it should be written differently.
okay. I'm not going to try and write down what the relationship is, but there is one, and it's hopefully quite simple. Okay, so this is the stringy point count, right? So this is the thing that we're going to try to express as some kind of p-adic integral. And kind of my next job is to explain how you extract a function on x that when you integrate, you get exactly this thing. And essentially what we're going to do is, well, we've got one obvious function on the inertia stack here. The function on the inertia stack is, well, there's two obvious functions, right? There's the whole thing, or you can kind of isolate this trace of Frobenius part. And the function we're going to get on x is going to be composing this trace of Frobenius part with a specialization map from points on x to points on the inertia stack of x. So p-adic point of x to mod p points on the inertia stack of x. So for that to work, I need to explain what the specialization map that we're going to use is. And that's the next task. What title did I give this bit? Orbifold integrals. Which I'm very likely to at some point slip up and call orbital integrals, which is a terrible, terrible mistake, but I'm almost certainly going to do it at some point. So I'm going to warn you in advance. Okay, so how does this work? Well, we've got our stack X, which is this finite quotient stack, and we've got this coarse modulo space X, which is the actual quotient. And living inside this, we have some open, dense subscheme where the map from M to X is eternal. So in other words, we take M, we kind of take the locus on which the action is free, and then we take the quotient there. So this is the sort of the nice locus of our stack, or if you like, this is the locus where the stack is actually a scheme, really. Okay, and then we can find a certain subset of the f points of the scheme X to be those OF points, such that when I restrict to, when I look at them as f points, I actually lie in this like nice locus.
I'm sorry, Chris. I've kind of confused myself.
Yeah.
So when I was talking, I had also an M and an X, but they.
Right.
No, I'm not saying you're not saying you should up my notation. But can you
Oh
remind me
no!
what's
Oh god, I've done a terrible, terrible thing.
what have you done?
I've done a terrible, terrible thing. My X at the very, very start was like the curve, the relative curve
Right.
that we've been using, and in the second, and ever since that opening bit, X has been the coarse modulo space of M.
So in some sense, your M is like my M. It's like morally.
Yes.
It's
Yeah, I
something
tried to
like
keep the M being your M.
Okay, but then your X is my M without the underline or something.
Yes. Yeah.
Awesome.
But yes, apologies. I've used X twice.
So like X is like the M, for example, M.
So for
SLN.
example, X is like M.
SLN without the
It's the coarse modulo space of the PGLN modulo stack.
Yeah.
For example.
Yeah.
So
And M is the
we've
fine.
been putting underlines in and taking them out.
Yeah.
So maybe that's the unambiguous way to say what I mean.
Yes. And then M is the thing without the word course.
And M is the thing. No, M.
Oh, sorry, it's PGL.
M.
Sorry, M is the gerb.
M is no.
No?
M is MLSLM.
Oh, sorry. Okay.
Yeah.
Oh, yeah, I see.
Yeah. Okay.
Yes. Thank you very much.
Right, and our specialization map, okay, so we've got, so inside the OF points of X, there's this subset of ones that when I look at them as F points, they lie inside this kind of nice part. And now, if I take one of these guys, I can do a funny construction to spit out a point of on the inertia stack of X. How does this work? So, my point, if I take, okay, let's take X in this XOF hash. So this is a point of X, and when I look at the corresponding F point, it focuses through the nice, it factors through the nice locus. So kind of what this means is that actually there's this gamma torsor lying over spec f, and there's a kind of there's a gamma equivariant map to M. And now I can take the integral closure of this inside this. I can put something here, and because everything's suitably nice, this map here is also going to be gamma equivariant. So what I get is a map from spec OTX mod gamma, the stack, into X, by taking this map and modding out by gamma. I can describe this a little more explicitly because Tx is going to be some product of abelian extensions of f, and then this is going to be isomorphic to this x L over f that we saw earlier. So gamma is going to commute some factors, and then the stabilizer of any one of these is going to be the Galois group of L over F.
But curly x L over F is nothing to do with curly x? Or
No.
Yeah, okay, cool.
It's not. Okay, so I have this morphism, and so by functoriality, I have this morphism, and we saw earlier how we've got a canonical point here, this y zeta that we saw here, and so we get k points on the inertia stack of x. And so we get a map that's called E in the paper. Which sends this point x to the image of y eta. Great, so this is our specialization map. So this is how we're going to cook up a function on x itself. And now I better tell you, if we're going to integrate this function, I better tell you the measure that we're going to use to integrate it. And in this situation, there's a natural one to choose, which is this orbifold measure. Now, what you can do is, if you look at this quotient map from M to X, you can show that there exists a unique Q Bay divisor, let's say D on X, such that if I look at Kx plus D, which a priori is just a Q Bay divisor, is actually Q Cartier. So that's the first condition, and the second condition is that Q upper star of Kx plus D equals Kn. So I have this divisor on X, and what you can do is, as I remember seeing, I think I remember hearing this in Arne's talk, but I was looking through my notes yesterday, and I couldn't see it, so maybe it was sort of said out loud rather than written on the board. But from this setup, you can produce a measure on the OF points of X. So D induces a measure on, let's say, XOF, which we call mu all. So the basic idea is that is you do the following. Right, this is a Q Cartier divisor. So some multiple of it is a Cartier divisor, therefore corresponds to a line bundle. This line bundle, when you restrict to the smooth locus of, say, the generic fiber, is going to embed inside the canonical sheaf, into some tensor power of the canonical sheaf. So you have an OX line bundle such that on the smooth locus of the generic fiber, is living inside a tensor power of the canonical sheaf, and this allows you to define a canonical get a measure. Yes.
Are you assuming that D is like effective or anti-effective? I don't see why does it live inside the
because L is associated to L is OX of RKX plus RD. Oh, okay, yes, no, you're right. I'm probably assuming it's effective.
Okay, I mean if it's not we can make a difference, I'm sure I'm just checking I understand.
Yes, yeah, sorry.
Awesome. Let's make two measures and take one off the other.
Yeah. I should probably say effective.
I mean, if we have a general one, we can write the difference of effectives and then take one measure minus the other, and maybe that also. I don't know if it's a group homomorphism.
I'm not sure.
Okay,
I don't know. Okay, so this is the measure we're going to use, and then the kind of key theorem is the theorem that describes the volumes of the fibers of E with respect to this measure.
Can I just
Yeah.
make a comment?
Yeah.
I don't have to write it again in my talk. So the first thing is that, so as you said, on the smooth locus or on this entire locus, the measure you assume the canonical boundary is trivial on that locus for simplicity. Then the measure analytically is really just given by integrating a section of that form. It's really explicit. And the second one is that if, say, your action of gamma preserves the canonical boundary, then you know that the complement of this x0 it will have codimension 2. And then D is just 0.
Okay.
It will,
so
for us, it will not appear, actually.
Okay, so it's D0 in the situation.
For us, yeah. If D only appears if you have actually a ramification device.
Great.
So this is sort of the most general thing, but
So the orbifold integral is the canonical measure.
right, except that it's not
Yes.
smooth.
Okay.
Yeah.
Okay.
I mean, the canonical measure is on the smooth, OF smooth.
Yeah. Isn't it? It's on XOF intersect XF smooth.
Exactly. Yes.
Yeah.
Yes. And there it's
Okay. So maybe. Anyway, we have the theorem that's in the appendix of the paper, which is a computation of the volumes of the preimages of this map. So, as it says, is for all y for any rational point on the inertia stack of x, the measure of the fiber of E over y is not quite this term that we're seeing here, but it's the term with the weight instead of the fermionic shift. So we get is q to the weight divided by the size of the automorphism group of y. And so as a corollary of this, once you've sorted out the formula that relates to the weight and the fermionic shift of these, this is a corollary of this, you can see that the stringy point count of x is, wait a second. So corollary is if we define a function on this subset of the OF points to C by first mapping by this specialization map to k points on the inertia stack, and then do this trace of Frobenius, to go into, let's say, QL bar or C. And if I take the composite function here, then the p-adic integral of this with respect to this measure is precisely the stringy point count. Up to some power of q. So what we get is the stringy point count of x with respect to this germ alpha is q to the dimension times the integral over the f points of x of this function alpha with respect to this orbifold measure.
Can you remind us what this weight is, this W of y?
Okay, yes. So this weight is what you do is at every so points of the inertia stack is going to split up into parts given by fixed points of a given element of gamma.
Yeah.
Right? And if you're fixed by an element of gamma, then you're going to get an action on the tangent space,
Yeah.
and it's essentially the sum of the powers of zeta appearing
Okay.
in the diagonalization of this
Okay,
action.
so it's inside the definition of this fermionic shift
Yes.
that occurred, right?
Yes.
Yeah. Okay.
Something like the fermionic shift is the weight minus the dimension of the like gamma invariant part of the,
Yeah.
something like this. There's some formula.
There are two notations in the literature. People do this integration business use weight, and this original paper of Hasse that they used was with the fermionic shift. To merge them.
Thanks.
Okay, so maybe I'll just very, very quickly say a couple of words about how this theorem is proved, just to give a very, very rough idea. The basic idea is that you reduce the case where this group gamma is cyclic, and then what you do is you near every point, in a formal neighborhood of every point, you diagonalize the action. And what this allows you to do is reduce to kind of gamma, a cyclic group acting on like AN diagonally, and you notice that sort of everything decomposes via this product, and so you kind of reduce to looking at a cyclic group acting on A1, and there you can kind of just write everything out reasonably explicitly. It's, I've made it sound much simpler than it actually is, but that's the sort of broad idea. But we need to press on. Okay, so we've kind of done part of what we want to do in the fact that we've got some function and we've got some measure and we've expressed these stringy point counts as some p-adic integral. But for this to actually be useful, we need to know what these functions f alpha really are, so we can say something about them. And that's what I'm going to do in the remaining 15 minutes or so. I'm going to definitely give one interpretation, and then hopefully, if time permits, give a second in the specific case that we're looking at. So I'm going to first explain how to relate this alfalfa to the Hasse invariant. And I'm going to start by just doing it in a very, very special case that, in fact, you can reduce the general case to. So we're going to look at curly x being this x L over f that we've seen a couple of times before. And we've got some gerb alpha on x L over f. And in this case, our function is just like a number. So f alpha of x is this trace of Frobenius. And I'm going to give, this is what we want to compute. And I'm going to write down a very big diagram that's going to tell us what this f alpha is. Okay, so we've got our gerb alpha living in the entire cohomology of x. And we have this transgression construction that takes a mu-n germ and spits out a mu-n torsa on the inertia stack. And now this inertia stack had this distinguished point, so we can pull back and we get a torsa on spec k, a mu-n torsa on spec k. Well, the Galois action of this on mu-n is trivial because we assumed that f contains all r roots of unity, therefore contains all n roots of unity. So this is homomorphisms from gal k bar over k into mu-n, k or f, it doesn't matter. And then I can evaluate on the Frobenius, and I get an element of mu-n f or mu-n k. On the other hand, I can do this construction that we saw a while back of taking a torso, pushing forward, looking at the chi subspace, and taking the trace. So this is kind of the trace of Frobenius construction that was a little bit convoluted. This lands in QL bar or C, depending on your choice, and then we have this chi here. And so I've written down this weird triangle, but it's kind of, this is just a complicated way of writing down the same thing lots and lots of times. So this bit commutes. And let me also say that this choice of zeta gives us an isomorphism between this and q mod z, the end portion in q mod z. Whew. So via this transgression and trace of Frobenius construction, I've got an element of q mod z end torsion. And I can get an element here in another way, right? Because what I can do is I can restrict this to the generic fiber. Sorry, these are all x, L over f here. Right, so I can restrict this to the generic fiber, which is just spec n. So this maps into the end torsion in the Brauer group of f, and then by the invariant, I mean this is an isomorphism, and then hang on, no, and then by the invariant map we have this. And the theorem is that kind of what you might hope is that this diagram commutes. This isn't quite the theorem, unfortunately. Theorem is that this diagram commutes up to some automorphism, let's say C of Q mod Z. So I kind of need to stick in some C, split these apart, and then I do get a genuine commutative diagram. And so as a corollary of this, what we can see is that because, you know, all this is completely functorial,
So even the C is, I mean, the C should be something very explicit, right? Everything.
No, the C is not something fairly explicit, unless I haven't made a mistake. I'll maybe say a couple of words about the proof in a minute, and then you'll see where the C comes from.
But to be honest, I think C, now we know it's that empty.
Ah, okay, great.
But at the time we didn't.
Okay,
It's
fantastic.
basically a kind of long check. We didn't really. And then the only thing we showed there that if you take different, somewhat,
Yes.
C's are compatible.
Okay, so the corollary of this is, okay, if we now know C is the identity, I'm gonna.
And this is not in the paper.
Okay, so this diagram computes.
Things evolve.
So the corollary of this, we can describe this function f alpha for a general, for the case of a general x, not just a special x L over f. So if we take m over f smooth, then for all x in x OF hash, f alpha of x is just the invariant of x star alpha. Essentially because we just kind of play the same sort of game as if we're given a point, then if we're given a point of x OF hash, we do what we did earlier to produce a morphism from x L over f to curly x. And then now, by functoriality, we can reduce to just this special case here. And so, like I said, I was going to say a few remarks about the proof of the theorem. So I think in the original version of the paper, the proof was essentially, if we pick one L, then this induces an isomorphism here, and, this induces an isomorphism like this, and now somehow if you go around the diagram, sorry, not this, it's over here.